this last example, we're trying to find the magnitude of the torque on the current loop shown in the figure. So the setup we have is there's a wire here. It's perpendicular to the page and the current flows out of the page. The current is 2 amps. There's a little loop here. It's not a very big loop. The diameter is 2 millimeters. It's carrying a current of 0.2 amps. The current is into the page here and out of the page here. So this is a little loop that's this way, kind of like the end of my flashlight here. So the current goes down on this side, up on this side. So it's a current loop that looks like this, flowing around this way. So we'd like to find the magnitude of the torque on the current loop. So let's think about how do we calculate torque. And we know that torque is mu cross B. What is mu? Mu is I of the loop times the area of the loop crossed with the magnetic field that the loop is sitting in. So where does that magnetic field come from? What is that B? So this loop is in a magnetic field that's created by this wire. We know that current carrying wires make magnetic fields. So this wire makes a magnetic field where this loop is sitting. So this B is the B made by this wire. So B is equal to mu naught times the I of the wire divided by 2 pi times R, where R is your distance from your wire to your point. So there's R, it's 2 centimeters. The direction of the magnetic field, so our magnetic field makes big circles around our wire, something like this. The orientation is, put our thumb with our current and we ask what's happening right here. Well, I see that right here at this loop, my fingers point straight up. So the direction of the magnetic field due to that wire is straight up. So that would be the J direction. Okay, so let's put this together. So we've got the I of the loop times the area vector, which is pi times r squared. The direction of the area vector is given as an orientation with the current. So we said that the current goes down on this side, up on this side. We make a circle with our fingers that reflects the current, and we see that our thumb points towards the left. So the direction is in minus I hat. That's going to be crossed with the magnetic field, which we just wrote down. And that direction was straight up. That was in the J direction. So that gives us minus I of the loop times pi times r squared times mu naught times I of the wire divided by 2 pi, oops, let's be careful with our r's here. This r is the r of the loop. 2 pi r. This r is your distance between the wire and the loop. So the radius of the loop is 1/2 the diameter equals 1 millimeter. Okay, so I of the loop times minus times pi r squared times mu naught I of the wire over 2 pi r times I cross j. I cross j is k hat. So all of our numbers we can fill in here. I don't think I'm going to write them all down, but let's just make a list so we don't go astray. So I of the loop equals 0.2 amps. R of the loop equals 1 millimeter, or 1 times 10 to the minus 3 meters. I of the wire is 2 amps. R is your distance between the wire and the loop equals 2 centimeters, 0.02 meters. And then that's everything. So then the torque vector is equal to minus 1.26 times 10 to the minus 11 k hat. Now, we weren't asked for the direction of the torque, but we decided to find it anyway, just because it's good to be able to do that. Let's ask if we know what that direction means. So minus k hat would be into the page. The direction of the torque vector is into the page. So what that tells us is that the orientation of the rotation is going to be to the right on the top and to the left on the bottom. So loop will rotate so there's the top of the loop where the current goes into the page. There's the bottom where it comes out of the page. That's your current loop. The direction of the torque vector is into the page. Oh, did I get that wrong? The direction of the torque vector, so the top goes to the right and the bottom goes to the left. I might have got my left and right mixed up there. So it's going to rotate this way. Okay, so these are your curled fingers. And then your torque vector is into the page. That's your thumb. And that kind of helps us with the last part of the question. What is the loop's equilibrium orientation? How could we lay the loop so that it wouldn't rotate? Well, we'd have to put it so that it were so that the magnetic moment is parallel to the magnetic field. And I suppose it could also be anti-parallel. The way to have that is the magnetic moment comes straight out this way. Your loop would have to be horizontal. So if you had your loop like this, then your magnetic moment would be this way, that would be mu. Your B would be this way, and in this case your torque would be 0. Or if you had your loop kind of flipped by 180, so your loop looked like this, now your magnetic moment would point up and your B would point up, and in both cases torque is 0. So if your loop is horizontal, then it's in equilibrium because it would not tend to rotate if we let it go when it was like that.